Hi, and welcome to the virtual Precision Ag Stop at the Milan No-Till Field Day. I'm Lori Duncan, an agricultural engineer working for UT Extension. This presentation is intended for producers and consultants at all levels of technology adoption. Hopefully, those with no or limited adoption of technologies will see the benefits of GPS on farm to determine if it's a good fit for them, and for those fully invested in precision agriculture to become more comfortable and increase their understanding of how GPS works. In this presentation, we will cover topics around 4 learning objectives. 1, what is GPS? How does it work? What are my options for use? And what applications could I start or expand my use for? GPS stands for Global Positioning System. This technology was created by the U.S. Department of Defense solely for military use. It took years to develop and became functional in the 80s, with the initial cost to the taxpayer being around $12 billion and a fairly high annual cost to maintain being $1.4 billion in 2019. Some interesting history there. Because of the sole use of GPS being for military applications, the US government had something called selective availability turned on that limited civilians' location accuracy substantially. Since then, there have been other methods created and used by the government to protect sensitive locations of military and defense applications. Selective availability was turned off in 2000, at which time we saw civil and commercial use of GPS skyrocket. So how much did our location accuracy improve with the removal of selective availability? This graph displays GPS error in meters on the y-axis and time on the x-axis. The specific time period is the day that selective availability was turned off, as you can see at 0600. With selective availability on, errors could range anywhere from almost 0 to 120 meters. With selective availability turned off, our errors now typically range from almost 0 to 10 meters and are more consistent, allowing us to use GPS to find our way on vacation or to help us on the farm. For those who fully utilize GPS, you might have noticed some other acronyms in a product brochure or manual. GPS is the United States Satellite Positioning System that consists of 31 functional satellites currently, but other countries also have their own. Russia has GLONASS with 24 functional satellites. The European Union has Galileo, created in 2016, with 22 usable satellites. And China has Beidou, that was begun in 2000, and they now have 42 functional satellites. All of these systems together make up what is called the Global Navigation Satellite System, or GNSS. Most receivers we purchase and use in the US to utilize more than one of these systems. This allows us to access more satellites for an improved fix more of the time. The US's Global Position System is committed to maintain at least 24 satellites that are in orbit around 11,000 nautical miles above Earth. There are 6 orbital planes, or paths, with 4 satellites each. These operate 24/7 and provide global coverage. We should have between 6 and 12 satellites in view at all times if we're in an open space. And these satellites use fast computers and highly accurate clocks to help us determine our location, as we'll discuss shortly. The technology behind all of the GNSS systems, such as the US's GPS, is comprised of 3 segments: the space segment, or the satellites, the control segment, which monitors and maintains satellites in their orbits, and the user segment, or the GPS receivers we have in our phones, tractors, etc. The satellites are continuously broadcasting information back to the control and user segments to ensure we know their exact position and time. We can determine the distance from the satellite to the receiver using ranging. The satellite broadcasts a signal that's then received by the user. Using the speed of light and the time difference between signal broadcast and reception, we can determine the physical distance from the satellite to the user. Then, because we know the position of the satellites via the control segment and our distance to the satellites, we can then calculate the position of the receiver. So how is our position determined then? And how many satellites do I need to have it fixed? If we were only fixed on one satellite, we would be able to determine where we were on a sphere. With two satellites, we can determine where we are on a circular area or where the two signals would intersect. With three satellites, we would be able to determine we were at one of two spots where all three satellite signals would intersect. With four satellites, there's only one possible point that we could be located based off the intersection of the satellite signals. This allows us to determine our location and our elevation. When our receiver is talking to at least four satellites, the receiver generally says it has a fix. So we know where the satellites are in space, we know how far we are to each one of them, and we're receiving a signal from at least four satellites. Then the GPS can simultaneously solve for latitude, longitude, and elevation. It's a pretty impressive piece of technology that we take for granted because it's fully programmed and automated, but it's still important to have a basic understanding and appreciation of how it functions. That all sounds really promising, but I still get some large errors sometimes. So what's causing these errors? There can be small differences in our clocks and the satellite segment clocks that can cause large errors. We're going to look at an example next. Interferences can occur as the signal travels through the atmosphere, and slight orbital variation of the satellites can cause errors. These are all errors that can be accounted for with some correction techniques that we'll discuss later in the presentation. Signal multipathing occurs when a receiver is too close to buildings or tree lines and the signal bounces off those before hitting the receiver, extending the time, thus the distance, from the satellite to the receiver. To show how significant these errors can be, let's look at this example. The satellites are orbiting around an altitude of 12,500 miles. The speed of light is 186,000 miles per second. So our transmission time should be 0.067 seconds. If the clock was off by 1/1000th of a second, our ranging distance could be off by 186 miles. This would cause major errors in our location determination. For our applications, that amount of error is unacceptable. That's where differential correction comes in. Differential GPS, or DGPS, works by using two receivers, one that is stationary and one that is roving around completing the task at hand. These two receivers are fairly close to each other, and thus the signals they receive from satellites should see the same amount of error. The stationary receiver has been accurately surveyed and is our reference station. Since it knows its true location, it uses this information to back calculate timing. It figures out what the travel time of this signal should be and compares it to what it actually was. The difference in timing is an error correction factor. The reference station then transmits this correction factor to the roving receiver that you are using so it can eliminate these errors. There are three ways this is accomplished: from the ground, from other satellites, or real-time kinematic correction. Let's assume our location is truly at 0, 0. With regular GPS in blue, we would see random errors all around our true location. With differential GPS in yellow, the amount of error is much smaller and less random. So let's talk about the three ways differential GPS can be accomplished. Ground-based DGPS works just as previously described, with reference stations transmitting error corrections to the user's receiver. The U.S. Coast Guard was one of the first DGPS services meant for marine navigation, but they'll be discontinuing as of 2020. Due to the increase in accuracy and availability of other GPS services, many were not using this service, and the Coast Guard no longer needed to maintain the network. Satellite-based services work in a similar manner, but instead of a base station talking directly with your receiver, The base station, or network of base stations, transmits the error information to a satellite in geosynchronous orbit, which then broadcasts these corrections to all user receivers that subscribe. The US government created a free satellite-based correction service called Wide Area Augmentation Service, or WAAS. Equipment and technology manufacturers have also created their own DGPS services that are paid subscriptions, like OmniStar and Starfire. Just like the US is not the only country with a global navigation system, we are not the only ones with satellite-based free differential correction services. WAAS was created to aid airplane navigation, takeoff and landing, and covers entire continental areas. Thus only improves accuracy to around 5 meters. This is many times good enough for car navigation or even large area soil sampling, but is not good enough for most of our precision applications. Equipment and technology manufacturers also have their own satellite-based correction services. These are subscription-based and can provide different levels of accuracies for a fee. Listed here are Trimble and John Deere services with varying degrees of year-to-year accuracy. Contact your dealer rep to discuss pricing and your actual required level of accuracy for your specific applications. RTK, or real-time kinematic correction, is the gold standard in precision agriculture. RTK can give sub-inch accuracy and reliability. This uses the same method as ground and satellite-based correction, but the base station or reference station is very close to the receiver you are using on your tractor or sprayer. Generally, this should be within a couple of miles. Some equipment dealers have their own local base stations that you can subscribe to if you are located near one, or they will also sell and install a base station on your own farm. There are also networks of base stations called cores, or continuously operating reference stations, to which you can subscribe. The Tennessee Department of Transportation has a network of base stations across Tennessee that can be subscribed to for around $500 a year if you are within a reasonable distance, around less than 25 miles of one of the physical reference stations. It's important to note the two different types of accuracy that are discussed with GPS technologies. Pass-to-pass is a measure of the relative accuracy over a 15-minute interval. This is the accuracy between adjacent parallel passes. Most DGPS services can result in fairly accurate pass-to-pass accuracies, which would be important for applications like spreading and spraying for that growing season. Year-to-year accuracy is a measure of repeatability, or returning to the same location after a longer time periods. This is a gold standard and is important for advanced precision ag technologies such as precision planting, fertilizer banding, installation of drip tape, etc. This colored map displays the level of accuracy you can expect from different DGPS services. With the free WAAS service, you can generally get within 1 foot of pass-to-pass accuracy and less than 5 foot of year-to-year reliability. Sub-meter and decimeter services describe different levels of the subscription-based services and can improve pass-to-pass accuracies down to 2 to 4 inches and year-to-year reliability down to 2 feet, depending on the service. As previously mentioned, RTK allows us sub-inch pass-to-pass and year-to-year reliability. These technologies and subscriptions are not cheap, and we recommend determining the actual required level of accuracy for your specific application before you pay for something you don't realistically need. Of course, RTK is great and will work for soil sampling and scouting, but it's overkill if you're not also using it for auto guidance or another high precision application. On the other hand, you could do variable rate application of fertilizer with loss correction, but you need to ensure any benefit of using that technology isn't lost because of poor location accuracy during your application. Listed here are some general costs of correction services. Please contact your own dealer for specific pricing. A WAAS-enabled receiver is fairly cheap. This would be like a cheap handheld GPS unit used for vehicle navigation or that some use for soil sampling. With RTK, assuming you purchase your own base station, you're looking at around $8,000 to $10,000. Satellite-based subscription services have a wide range of costs, but generally the receivers will cost between $500 and $4,000 and the service up to $1,000 a year. DGPS enables you to collect spatial data and also to drive spatial applications via a controller. If you are paying for a DGPS correction service through an equipment dealer, you will also likely have access to a computer-based platform called a Geographic Information System, or GIS, to display your GPS data and to make decisions based on spatially collected information, such as yield data, soil sampling, or soil EC, to name a few. These software systems do have a learning curve, but many consultants are proficient in these and will handle this aspect of data collection, analysis, and application. There are all types of spatial data we can collect by using GPS technology, including imagery, soil information, topography, yield data, and crop health indices. Management decisions can then be based off of all available information for a specific location in the field. There are many precision agriculture applications that can be accomplished through use of a good DGPS signal. In general, these include resource mapping, navigation, yield and crop monitoring, and application of inputs, among other things. We'll briefly look closer at a few of these applications that could be potentially beneficial to our producers and consultants. Yield data from a yield monitor can be some of the most valuable information that can be garnered from a GPS-enabled technology. This data quantifies yields in specific portions of the field and can give us an idea of future yield potential on a spatial basis. This information can then be used to drive future variable rate input applications, such as seeding, fertilizer, lime, and herbicide applications. Auto guidance has been widely adopted due to the decrease in operator fatigue and improvements in production efficiency. Fully integrated systems can come standard on newer pieces of equipment, but there are also several aftermarket retrofit options for older equipment. Automatic section, or even more precise, nozzle control is available for planting, fertilize, and spray applications. Generally, a prescription is written in a GIS software that tells the onboard controller where and how much input to apply. This is especially helpful in the non-square fields we farm east of the Mississippi River, allowing us to turn off application in non-cropped areas while still applying in the cropped areas. This leads to lower input costs and less off-site movement of fertilizers and herbicides. Section and nozzle control is also used in precision irrigation, where we can vary the rates and timing of water applied on a spatial basis. This is especially beneficial for fields with substantial soil type differences. GPS machine control is another important application, not only for construction, but also for precision leveling or any groundwork done on farm to alleviate drainage issues or install drip tape. There are also applications in precision livestock management, such as the use of GPS collars on cattle for the use of tracking, animal health data collection, and pasture management. Applications for GPS in agriculture are limitless. Just to recap what we've covered in the last 20 or so minutes, we learned what GPS is, the basics of how it works, and why we need differential correction for precision agriculture. We covered some of our purchase and subscription options to improve accuracy. Please contact your equipment dealer or service provider for more up-to-date and specific pricing. We also briefly covered some applications from basic to advanced for GPS in agriculture. I hope this presentation provided some helpful information on GPS technologies, no matter where you are in your journey of technology adoption. If you have any questions regarding any precision ag technologies, feel free to contact me at the email address or phone number listed here. Thanks for tuning in and best wishes for the rest of the growing season.